Take a completely straight pen and drop it into a glass of water. Look closely at the liquid line. The pen appears to snap into a sharp angle exactly where it crosses the surface. But if you pull that same pen back out, the plastic is undamaged. The physical object hasn't changed shape at all. To understand why this happens, we have to remember that human eyes don't actually see physical objects. We see the light rays that bounce off those objects. In empty space, those rays travel in straight paths directly from the pen to our eyes. The question is, what happens to that perfectly straight light path when we pour water into the environment? Notice how the straight vectors suddenly warp and disjoint right at the boundary line. If we remove the pen from the diagram entirely, we can isolate the actual mechanism. The break in the pen is an optical illusion, but the bending of the light as it travels toward the observer is a physical reality. This diagram shows the two separate environments the light must travel through. We have the dense water in the bottom section and the much thinner air in the top section. Physicists measure this optical density using a value called the refractive index. You can think of this index as a strict speed limit. Water has a higher index, meaning a lower maximum speed for light. Air has a lower index, allowing a much higher speed. Because liquid water is optically dense, it creates resistance. A light ray traveling up from the bottom section moves at a slow, restricted pace, similar to a person trying to walk through a crowded room. The moment that light ray crosses the boundary and escapes into the thinner air, the resistance drops. The light experiences a massive and immediate acceleration. Every time light crosses a boundary between two different refractive indexes, a change in velocity is guaranteed. To measure exactly how this speed change affects the light, we use a tool called the normal line. This is an invisible, perfectly vertical reference line drawn exactly perpendicular to the boundary surface. Let's track a single ray of light bouncing off the submerged pen tip. It travels diagonally upward through the water, heading straight for the point where the normal line meets the surface. Right as the ray hits that exact intersection point, the lower refractive index of the air takes over. The acceleration begins instantly, but because the ray hits the boundary at an angle, one side of the light wave speeds up before the other. This uneven acceleration physically forces the trajectory to flatten out, pivoting sharply away from the vertical normal line. That dual action process is the precise definition of refraction. The light changes speed upon entering a new optical density, and that change in speed forces it to change direction. Now, we follow that newly angled light ray to its final destination as it enters the human eye. This is where the biological flaw occurs. As the brain begins processing the image, it relies on a hardwired, unyielding assumption. It assumes light only ever travels in perfectly straight lines. To figure out where the pen is, the brain reverse engineers the path. It projects a straight line backward from the exact angle the light hit the eye, completely ignoring the bend that just occurred at the water surface. Because it traces this shallow angle backward, the brain's projection line stops at a false location. It renders a phantom pen tip at a significantly higher elevation than where the true object is actually resting. The bent pen you see in the glass is a constructed image. It is an optical illusion generated strictly because your brain insists on overlaying a straight line onto a genuinely bent ray of light. For your Class 10 exams, this infographic details the 3 critical rules you need to master. First, refraction is the bending of light. Second, a higher refractive index equals a slower speed. And third, transitioning between any 2 different mediums will trigger that bend. Grab a glass of water and a pencil at your own desk. Try looking at it from different heights to observe how optical density shifts the angle in real time. Make sure to subscribe to BIJU at EDUCATOR and drop a comment below letting me know which physics experiment we should deconstruct next. Understanding the physics of light gives you the tools to decode the brilliant illusions reality presents to our eyes every single day.